Okay, it's day 3 of ionic compounds. So let's get started. If I can get it moving. Okay, so we've talked about how to name ionic compounds, how to write formulas, what they are. They're made up of metals and nonmetals. Now we're going to talk about the properties of these types of compounds. Many ionic compounds will dissolve in water. They'll break apart in water. Think about salt. Salt dissolves in water. So there are a lot of ionic compounds that will dissolve in water. Solutions, like when you mix an ionic compound in water, it's considered a solution. Solutions of ionic compounds, they conduct electricity. Okay, so those ionic charges, they can move. Sorry about the bell. When an ionic compound is dissolved in water, they do conduct electricity. These things are called electrolytes. They've got a special name. Electrolytes are things that are found in Gatorade that help replenish the salts in your body that you lose when you sweat, when you exercise. So that's what electrolytes are. They're just ionic compounds dissolved in water. If you look on the side of your Powerade, usually you'll see some of the ions that are dissolved in the water in the solution of Powerade, and you'll recognize some of them. Ionic compounds have very, very high melting points. It takes a whole lot of heat to break them apart. Okay, it takes a whole lot of heat to break them apart. When they're molten, or when they are finally in that liquid type stage, they'll conduct electricity. Ions can move. Those ions will carry charge in solution and when they're molten. They exist in something called a crystal lattice structure. If you see down here at the bottom, this is a really pretty crystal, but they kind of look like that when they dry. They exist as a crystal. They have a repeating pattern of, like up here, they have negative, positive, and it goes on, and they're all put together in a very specific way in that geometric shape, and they form what looks like a crystal. A metallic bond, we talked very little about metallic bonds, but metallic bonds are the attraction of metallic delocalized electrons. So when you have a metal, their electrons are shared. They're said to be in a sea of electrons. They form lattices in the solid state similar to an ionic crystal, but we say that their electrons are in an electron sea model. Down here at the bottom, that's a really good picture. It gives a good illustration of what we're talking about. These the valence electrons will come off, and they'll be shared in between all the different metallic ions, metallic atoms in that compound. They can move freely from atom to atom. They're not bound tightly to any one particular atom. We say that these electrons, these little valence electrons that are running around here in this electron sea, are called delocalized, meaning that they're not localized to any one atom. They're delocalized. They're allowed to move around freely within that structure. Properties of metals, again, more metals. Properties of metals, they have high melting and boiling points. They're malleable. Metallic compounds tend to be malleable. They can be bent. They can be shaped, hammered into sheets. Ductile means that they can be made into a wire. Copper wire, all right, is made of copper. So they're ductile. They can be made into wire. They're very good conductors of electricity, and they tend to be shiny when you polish them up nicely. An alloy is a mixture of metals. Jewelry is a mixture of metals. My rings, they're not all gold. Gold is really soft. So what happens is that they make an alloy of gold, and they mix other metals in with the gold to give it strength, so that it doesn't bend and get bent very easily. The higher the carat, like 24 karat gold, the more gold is in it. So it'll tend to be softer and more easily damaged. But 10 karat gold won't be. It'll have less gold in it. Still pretty, it's still gold. Not quite as shiny as 24 karat gold, but it's a little bit stronger too. So you have that trade-off, the strength for the kind of the shiny, pretty that you're buying the gold for. Some other examples of alloys. Brass is not an element on the periodic table. It's not Br. It's not bromine. Brass is made up of copper and zinc. Bronze, like the bronze medal in the Olympics, is made up of copper, zinc, and tin. 24 karat gold, like I was talking about earlier, about 42% gold. It's got some silver and some copper mixed in there too. Pewter is kind of a grayish color. Kind of looks almost like silver, but maybe a little more gray. It's made of tin, lead, and antimony. All right, acids. I'm going to teach you how to do some acid nomenclature now and writing formulas for acids. The reason that we start you now learning how to name these acids and write formulas for them is that you have trouble with them all year. And the last unit that we do of the year is an acid-base unit. And so we're hoping that by the end of the year, you'll be able to write formulas for acids and name acids pretty well. Acids that we'll study in this unit are pretty easy to recognize. They'll contain one or more hydrogen atoms bonded to it. So all acids in this case, all acids in our class will start with a hydrogen. An acid is a compound that dissociates in water and produces hydrogen ions. Let me see if I can draw them here. Get my little pen going over here. Ooh. There we go. All right, so they'll form different types of atoms, or different types of acids. H2SO4, HCl, HNO3. Okay, you'll recognize these are acids because they have the hydrogen in the front. Okay, the only thing that has a hydrogen in the front that we'll use, it's not an acid. Water. Water is not an acid. Actually, it can be an acid or a base. So, but in our case, it's not. All right. These are acids. They start with hydrogens, and when we put these acids in water, the hydrogen will dissociate. The whole thing will dissociate, and the hydrogen will come off. So this hydrogen will break apart in water. These two hydrogens will come off in water. So will this one. All right. The more hydrogens that dissociate from an acid, the stronger the acid. So we'll talk a little bit about that too. And no, I don't want to keep that. There we go. Binary acid nomenclature. Binary, remember, means two. A binary acid will have just two elements. So it'll be a hydrogen and one other element. The prefix that you'll use when you're naming these binary acids is the prefix hydro. So you see it right here. You'll put an ic on the end of the second element. So sounds complicated, not really so much. So all of these down here are binary acids. Why are they binary acids? Well, because they have two elements. When they have two elements, the way you name them is you start by writing the prefix hydro. Okay? Then you find whatever the second element is. In this case, it's chlorine. But instead of chlorine, you knock off the ending and you put IC, chloric acid. Okay? So hydrochloric, there's the suffix IC, and you follow it up by acid. So this one right here, it's a binary acid because it has two elements in it, hydrogen and one other element. Start by writing the prefix hydro. And since it's bromine, we won't put hydrobromine acid, it'll be hydrobromic acid. You knock off the ending and you add the IC suffix. HF here is a binary acid because it has two elements in it. Start out by writing hydro and then knock off the end of fluorine and use fluoric, IC, on the end. So this is hydrofluoric acid. Naming oxyacids. Oxyacids are a little more complicated because they have a polyatomic ion in them. These will have a hydrogen plus a polyatomic, so there will be 3 or more elements that are in this compound. Count the capital letters. Please count the capital letters. It's not that hard. Let's see. If the ion, the polyatomic ion, if the ion ends in ATE, you're going to change it to IC. So let's say it was sulfate. Sorry about that. My pen going down here. Let's say it's this. Okay. I know that SO4 is sulfate. Okay. That means sulfate. These oxyacids don't get the prefix hydro. All you do is if it ends in ATE, you change the ending to IC. And then you add the word acid. So H2SO4 would be sulfuric acid. No hydro. And since it ends, the polyatomic ends in ATE, you change the ending to IC. Here, HNO3, NO3 is nitrate. nitrate gets changed into nitric, so this is nitric acid. Okay, it's polyatomic, or it's an oxyacid, doesn't get the prefix hydro. H2SO4, SO4 is sulfate. This becomes sulfuric acid. Okay, because it has the sulfate ion. ATE becomes IC. So the way you remember that is I ate something icky. ATE turns into IC. I ate something icky. So try that to remember those. Let's go to the next kind. Okay, if the polyatomic ion ends in ITE, you change the ending to OUS. And here's what you're going to remember for that. Snake, oh, I have my pen going. There we go. Snake bite is venomous. If it ends in ITE, you change the ending to OUS. So here we have HNO2. NO2 is the polyatomic ion, and it's nitrite. So instead of nitrite acid, doesn't get a hydro, okay, since it's nitrite, it becomes nitrous acid, OUS. ITE becomes OUS. H2SO3, SO3 is sulfite, so you change the ITE to OUS, so this is sulfurous acid. Okay, no hydro for these oxyacids. No hydro at all, and we'll do a lot of practice for you. Okay, I don't want you to think I won't practice with you. Okay, so one last thing before we end this up, I'm going to teach you guys how to calculate molar mass. Molar mass is the mass in 1 mole of a substance, and a mole is a really big number. A mole is, oops, I don't have my pen going. I'm trying to write on here. A mole is 6.02 times 10 to the 23rd of something. So in this case, it could be atoms. Think about how big that is. That's 6.02, and then you got 21 zeros behind it. That's a lot of atoms. So we have to use molar mass to talk about the mass of atoms, because it's hard to fathom how small an atom is. So we have 6.02 times 10 to the 23rd of those atoms in 1 mole. So we count things using the mole. Molar mass is not complicated. Molar mass is on your periodic table. Molar mass is the mass in 1 mole of any element. The unit is grams per mole, or G/mol. Mole is abbreviated MOL. I know, all you do is knock off the E, but that's seriously the abbreviation. Essentially, the molar mass of any element is simply equal to its atomic mass on the periodic table. Let's take a look. Okay, so we're going to find the molar mass of these things. Find the formula first. Okay, what's the formula for zinc? Well, it's not a compound, it's just an element. So its symbol, put my pen back on. There we go. Symbol Zn. Okay, we're going to find the molar mass of zinc. So get my periodic table. And you don't usually see me in class. You'll see me a lot with my glasses on, but not on the videos usually. But I can't see this without them. So zinc, right here on your periodic table. It's not a transition metal. It's a transition metal that's always got the same oxidation number. So its molar mass is 65.38 grams per mole. That's the number on the periodic table. Okay, how about 2, or B? Symbol for chlorine, Cl. Find it on your periodic table. It's over here in the halogens. Okay, chlorine. What's the molar mass for chlorine? Let's see, 35.45 grams per mole. Okay, calcium bromide. You know how to write that formula. Calcium is Ca, and bromine is Br. Calcium has an oxidation number. It's in group 2, so it's always +2. Bromine is in group 7 or group 17, so it has a -1 oxidation number. Crisscross those using the subscripts, and you get CaBr2. So now to find the molar mass of that, you find the mass of calcium on your periodic table. It's in group 2. It's 40.08. And bromine, but there's 2 of them. So find bromine. Bromine right here, 79.90 times 2. 79.90 times 2, 159.8. Okay, so what do you think we do? Last step, add them together, and that's going to be the molar mass. So plus, and I get 199.88 grams per mole. Ta-da! Okay. How about this one, magnesium phosphate? Symbol for magnesium, Mg. Symbol for phosphate, ATE, tells me it's a polyatomic ion, so I have to go back to my list. PO4. Oxidation number for magnesium, it's in group 2, so it's +2. Find PO4 on your polyatomic ions list. Its oxidation number is -3. So we crisscross them, keeping them on the outside of those parentheses, and you get Mg3 PO4 2. Now we need to do the molar mass. This one's a little more complicated. We're going to need a little bit more room. So we'll start over here with magnesium. So it's going to be magnesium times 3. So let's see what is magnesium times 3. Find it right here in your periodic table. 24.30 times 3. And I get 72.9. Okay, so this kind of works the same way that parentheses do in math. So the 2 that's on the outside of the parentheses gets distributed to each element inside the parentheses. So 2 times 1, understood 1 there for phosphorus, is 2. So there will be 2 phosphorus atoms. P times 2. Okay, phosphorus is over here. I'm trying to get it. There we go, right there. And its molar mass, 30.97 times 2. And I get 61.94. Okay, how many oxygens are there? 8. So oxygen times 8, 16 times 8 is 128. Last step, add them all together. So plus 72.9 plus 61.94, I get 262.84 grams per mole for that magnesium phosphate. Okay, so what do you think? Molar mass, easy, hard? Not that hard. It's one of the easier things that we'll do, believe it or not. Okay, so we'll do a little bit more practice in the homework tutorial video, so be sure to do your homework. It's the only way you're going to learn it.